Good. So this is a senior design project by Agron Gemajli and Shivam Patel, and I oversaw it. And so I want to talk about a low carbon proof of work blockchain, which I realize is a lot to say. But first, I want to define a little bit about blockchains, just so we're all on the same page, and talk about the proof of work particular ones. And then we'll look at our series of other interesting, what I'll call low carbon blockchains. Some of them are, proof of work, some are proof of stake. We'll talk about some of the goals and aspirations we have had. In addition, there's a few things that that really would make our proof of work blockchain complete, which we're not able to put in the paper, but that's something to look forward to. So this is a general overview of blockchains, but the big thing here is in this box right down here. We are going to talk about proof of our low carbon dioxide blockchains in the sense that we're not going to burn that much electricity, or at least relatively that much, by computing jobs that must be computed anyway as what we call our proof of work. And we're going to do this using proof of virtual machines. And we'll get to these details in a few moments. So one of the big motivations for blockchains is we can cut out the central bank in some sense, or the central entities. So central authorities can be very useful and are very important in many contexts, but they can also create catastrophic failures if they go crazy or if they get out of bounds. So one of the great innovations in blockchain is let's make these complicated transactions peer-to-peer and just about automatic, so we don't have to worry about this central source of risk or of power. So what precisely are we talking about when we say proof of work? So a proof of work, just at a very high level, we'll define a little bit of these things as we go. I wanted to put this up front to get things going. So the idea of proof of work blockchains is anybody who suitably installs the right software and that sort of thing can help build the blockchain potentially. However, or that's the but here, we have to be careful of people who abuse and abuse the network, and therefore we have to have a mechanism to throttle network abuse, okay, or abuse of the system, let's say. Okay, for example, if we just said, hey, anybody who can open a port into this network and make some money or can build the network, one person can open 60,000 ports. And that may be interesting, but that may also plug up the network. So we want to throttle that use and abuse of the network. And this original idea is actually go back to Moni Nauer and Cynthia Dwork, and as well as Adam Back. So they had some really good ideas building both thwarting or proof of work, and they had some great ideas about putting in blocks in case of both of these groups. But in any case, the idea is a bunch of miners can come in. And that can be anybody who suitably installs software, and some of them must get paid, or at least one of them must get paid eventually. Otherwise, the whole network will go away. I mean, if you don't compensate somebody for their work, they quickly go away, as we all know. So the proof of work is you do some work, but that work really is there to thwart attacks or throttle the use and abuse of the network. And when you do the work, you have some chance of actually getting paid, maybe hopefully a decent chance. And so that is the idea of proof of work at a very high level. Now, the proof of work typically uses message digest hash functions. There's other proofs of work out there as well, but this is a typical proof of work. And the challenge is, as I say at the top, it burns a lot of carbon dioxide. It burns a lot of electricity. Now, electricity, of course, is a very precious commodity, and I see electricity largely as fungible. It can be traded. Many countries and many regions of the world trade electricity, whether it's generated by nuclear power plants or the sun or fossil fuels. But on average, because of the fungibility, if a lot of electricity is being used in the current global mix of electricity, we're probably burning some carbon dioxide, at least some portion. So the main thing that burns a lot of this is called it's called a message digest hash function. This can take a large amount of input text, perhaps up to a gigabyte or so, and it can compress it and give it a fingerprint that can be very small. For example, here's a very small fingerprint. We have simply 10 things to choose from, the digits from 0 to 9. So then, of course, a good message digest hash functions illustrates something that would be called the avalanche effect. As you change a single bit in the input, then it completely uniformly changes, or appears to uniformly change, the output. Okay, now, this is a deterministic function, h, but if you randomize the input just a teeny bit, it seems to really splash uniformly on the output. But of course, the likelihood of a collision with this tiny output set, 0 through 9, is 1/10. Okay, so if we do a little bit of randomization of our input through that deterministic hash function, we'll get one of these 10 digits with the same likelihood. And a collision must, of course, if we have 11 inputs, a collision must occur by the pigeonhole principle. Now, in the case of message digest hash functions, though, the idea here is we have a very large message with lots of text, and we compress that or get a fingerprint that is of size 256 bits. Now, 256 bits, hey, 256 bits I can read off if I need to, or I can turn those into hexadecimal and read them in, not too much, and divide the 256 by 4 digits. So the likelihood of a collision here is 1 over 2 to the 256. Now, 2 to the 256 is, product of a couple thousand smaller than, or I should say, a few thousand, within a couple orders of magnitude, let's say, of the known particles in the known universe. So that's actually a pretty big number. Completely infeasible to enumerate all the values in that number. Completely infeasible to do computations of close to all the number of particles in the universe. So the likelihood of a collision occurring if you pick two random and uniform inputs to put into a deterministic function is super big. Again, impossibly big. And so the idea of these hash functions is we want to get them in a certain range or a certain value. And of course, to do that takes lots and lots of work. Okay, as I say, we get to fiddle around with the input, and we may have to fiddle a lot with that input. And that's the work we do in our proof of work. And that's what costs the carbon dioxide. Now, there are other challenges or puzzles for blockchains. People hunt prime numbers and other interesting things, but this is the typical one, or the perhaps message digest hash functions is the most used. So a block chain is simply a hash function, uses that fingerprint we just saw, or that hash function we just saw, to compute a value for each next block, which is not reversible for lots of reasons. But one reason is it compresses everything into a fingerprint. But and so if somebody comes along and challenges, for example, B2, that they have the right B2, they'd have to show that their hash function actually from B1 made some sense, and why they did that and how they did that. So this leads to the notion of cryptocurrencies, which are a key role in all of these things. And I'm mentioning this because we'll talk a little bit about this in our proof of low carbon dioxide, or a low carbon dioxide blockchain. So cryptocurrencies are a form of money that is insured not by a central bank or a law, but in fact are insured by cryptography. So a lot of this whole blockchain idea is a cryptographic focus. And there's a couple of important terms here. So seigniorage tells us that the people who do the minting, that is to say, the people who are helping maintain this blockchain, are the ones that get paid with the cryptocurrency. And you have to pay somebody, and you have to have some likelihood of being paid, or we'll all walk away. So our basic idea of the low carbon blockchains comes from a long series of other ideas. And as usual, in particular, the first glimpse of something in this direction was volunteers sharing idle computing time. Now, the first one I'm aware of and could find in literature was computing Mersennine primes. So, some folks went out and decided, a student from MIT, and later on now a well-seasoned developer, went out and decided he wanted to have a system that hunted for Mersennine primes because it's very interesting, and perhaps there's even some uses for them other than great mathematics. So he got volunteers to share idle computing time. And then, of course, there was SETI, or the Search for Extraterrestrial Life. There was a protein folding program as well, where people would have, hey, I leave my computer on all weekend and don't do much with it. Why not let these other computational engines do something with it? So that, in a way, was saying, hey, my computer is burning carbon dioxide. I might as well use that carbon dioxide for something that somebody values. Now, that's a great idea. Of course, in reality, you might increase a little bit of the carbon cost on your computer if you loan somebody else your CPU cycles. For example, you might run your disk more than you would if it was idle. The screen might even turn on, or just it may even do a lot more work in terms of just transferring data around, and may even use your GPU, etc. So the original idea is wasn't really focused, I don't think, on lowering carbon dioxide per se, but it actually did have that consequence, provided that somebody really was going to compute Mersennine primes, or somebody really wanted to compute SETI and it was being paid for. And if you didn't put it on people's idle time, well, then it would be done anyway. If that was the case, it may have been, I'm not really sure. I don't think so, though. Then, in fact, we've saved some carbon dioxide. And also, and more recently, after this volunteer, it became the idea of distributed science, and this actually added a dimension to volunteering shared idle time. So the distributed science group, there's a number of blockchains based on this, we'll discuss in a few moments, was that not only do we often have scientific projects, and those projects have a couple of very special needs. We want to be able to verify them. Okay, so if I claim I did an experiment, you want to be able to verify it in your lab, and we want to reproduce it. I want to be able to, verify it and see exactly the same outcomes with the same inputs. And maybe we could put that on something like a blockchain and the blocks to verify it and make it verifiable. In addition, if it's a blockchain, different than the volunteering computing that we just discussed, a distributed science system could actually generate money, maybe through like a blockchain type currency, a cryptocurrency, and that could be used to defray the cost. Now, science also is great, and I love engineering and applied science and pure science too, for sure. But the challenge there is some of these experiments, if you end up paying for them in the blockchain, they may actually advance our understanding. They may help us out economically. They may help us out in many ways, but they may have not occurred. They may not have occurred unless you had the blockchain, which is okay. I mean, I have no problem with that. Again, I love the science and engineering. But anyway, so then we were looking at areas around here, and I went back and reviewed the literature to find it more depth. But we came across that maybe there's even more general things that can be done. And this wasn't unique. This idea was not unique to us, it turns out. But maybe there's more general computation that can be done for lowering the carbon footprint, that is to say, lowering the amount of energy. And that could be done by let people find problems they're going to do anyway on their own networks and just dump them to our blockchain, so to speak. And we could turn those somehow into a proof of work. That is to say, if you want to, I've been in a few places where we were computing our accounting data. Sometimes this would run, overnight, big complicated computations, and it's every month, or in some cases even more often, every night, churn through your accounting data, and we have to compute it anyway. Maybe the thing to do would be to have a blockchain compute it as a proof of work, which means since we had to compute it anyhow, we could shut down our servers at night, or hopefully we would do that. So again, we're back to our hypothesis. Can we find a way to compute jobs that must be computed anyway as proof of work? And we came up with the proof of virtual machine. And again, this is maybe not the most radically new idea, but it is useful. So here's some what I call low carbon proof of work blockchains. Some of these blockchains mention that they may be lower carbon. Several of them really are proof of stake, which proof of stake means you have to have a stake in the system. I think that's okay. I don't want that becomes a difficult discussion, proof of work versus proof of stake. I believe that proof of stake very easily becomes a centralized system by the stakeholders. Not always, and some proof of stakes have done some clever ideas to prevent that. And of course, some proof of work systems like Bitcoin has been swallowed up by entire countries to be computed, or large groups, which in a way is also, you could argue, is a proof of stake. So there's some fuzzy borders there. But just to discuss a few of the key, what I'll call things that are heading towards low carbon blockchains, one is grid coin, and this is a proof of stake system that actually has its own coin. Several of these have their own coins, in fact, and that rewards volunteer computing. And this comes from the Berkeley systems that launched SETI, the search for extraterrestrial life that would try to interpret signals coming from space. Very interesting. Golem, which is from Switzerland, and this is a very nice one. And what they also do, so they want to really commoditize CPU cycles or sell CPU cycles to different folks, through a blockchain. And what they require is a kernel virtual machine to be installed on your computer. Almost all modern systems you can do this, or I should say modern desktop machines or large laptops. You can do this with KVM requires a virtualized chip, which is fine, but you have to actually install this on your system, which is great, and then there's iExec, which generally computes assets and uses smart contracts. And so the idea here is they do general compute assets. That could be CPU cycles, that could be data, that could be supplying other services that computers supply through smart contracts, which I think is actually a pretty general case. Sonam is cloud-based. Again, they let you buy into CPU cycles or data. And this is really, they talk really about it being in the fog, which is pretty true. It's not, in the cloud per se. I mean, you could put it in the cloud, but it might as well be in the fog on the edge of the cloud, so you can do the computation maybe close to home. And that would also, of course, potentially help reduce some minor amounts of carbon dioxide burning. Okay. They also have their own cryptocurrency. Chain fast. Okay, this is functions as a service. So this is really a getting CPU cycles through a how should I say it, through a serverless system. So we're really literally saying, okay, if you want some CPU cycles, if I have a serverless system, throw me your job, I'll run it there and maybe save some cycles. And the idea of how these save cycles is they're supplying compute power or data or something like that that's useful for proof of work in the end of the day. Now, sometimes it's proof of stake. That is to say, there are stakeholders there that allow you to compute on their systems. So I want to jump into our system so that we can talk about it. So some of the tools we use now, these tools are not unique to us. For example, if you look at Golem, some of their work, they talk about using Docker containers. So Docker is a containerizing system. What that does is that gives you a operating system level virtual machine. Now, there's issues with that, without a doubt. So, for example, if you run a Docker container, they're maybe a little bit less secure than running a fully virtualized container because it's literally sharing some of the underlying infrastructure. But in any case, we use Docker containers to be as our compute engines where we're going to compute our proof of work. And then to manage these Docker containers is classically using Kubernetes. Now, we connect our Kubernetes instances, and everything is run from a system called Scupper, which is a relatively new Apache product. Scupper connects Kubernetes instances. So our system basically says, okay, if somebody hands us a job, we'll have a website, and we actually have this very, very simple website, a trivial one. It doesn't have its own IP address. It lives on our own desktop and our GitHub repo. And you can give it a simple job. The simple jobs right now we have are made up, but you can take that, hand it to the front end that will talk it through Scupper. Scupper distributes to different Kubernetes networks. So you could offer a Kubernetes network and somebody else could offer a Kubernetes network. And we could actually serve loads to them. And if they complete the jobs and send back their solutions and they're validated, and we'll talk about that, then we could say, hey, that person supplied, or that Kubernetes network supplied 10 virtual containers for an hour, and therefore they get a lottery ticket. A lottery ticket to win some money or to win some resources. Okay, the money they could win could be a token or, in fact, another currency. So the idea here is to effectively have and these ideas all look like they're in other places, in fact, but we're trying to put them together. We have a website hanging off, talking to a Scupper network, which runs some Kubernetes networks, connects to them. They runs the Docker networks to run the jobs, and then if 100 Docker containers are being run, different jobs or even similar jobs, then as soon as they validate that they have been done, and that's tricky, by the way, they validate they did their compute, they promised, then we say, okay, these 100 machines are now in a lottery, and we can randomly pick a winner from there and pay them. Okay. Now, we can also even ask people who deposit jobs in the front end here to pay some money in cryptocurrency or otherwise to have their jobs done. We don't have to do them for free as simply proof of work. So this is roughly what our system looks like. And the one challenge, so there's a couple of challenges here. One is Scupper is not consensus-based. So this is truly not what I would call a consensus-based blockchain proof of work. Okay. Kubernetes also, the instances we're running are not consensus-based. The Docker containers don't, I guess, have to be. And so we have our system here, although it's not, and we implemented this, in fact, the students did, I should say, Agron and Shivam did. But in the end of the day, the system itself has some work to do to get it truly a blockchain system. And the biggest glaring issue is Scupper. There's a few other issues. How do we verify? So I send a couple jobs, through Scupper to Kubernetes, to some Kubernetes instance, and that Kubernetes instance hasn't really maintained its Docker containers or anything else, or even it stops them early to make more money by computing something else to get in another lottery. Well, there's a couple of ways to verify the Docker computations. In fact, Golem and Sonam and a few of the other networks we've looked at build reputation scores. So if you are a person offering your Kubernetes network and you keep stopping jobs early or something else, your reputation will get very poor. So you're not going to get many jobs served to you or any job served to you. Likewise, the network nodes could get rated. So could the people asking the jobs for compute. So if I was to send a bunch of jobs in, and these jobs made machines wild and thrashing them and everything else, maybe the system doesn't want them either. And this is, again, you can go back to Golem and a few of the other systems that were developed before ours that use this two-way reputation verification. But to verify, there's a couple of issues. So to verify the configurations of Docker containers is fairly easy. They come with fingerprints. As long as it's a standard container in the Docker repository, you can just pull it down, check the fingerprint. We can even put the fingerprint on a side chain or somewhere else. We might have service level agreements on the side of the people supplying the jobs. If somebody supplies a job, we would hope it isn't giant memory hog or something else that clobbers your team's Docker containers. And so we have to be careful of that. But when we can verify the computation in a number of ways, one of the key ways that we were realizing was to have redundant computation. Now, what that means is if we get a couple of work jobs that people submit that are actual things they're going to compute anyway, whether or not our network is around, they're going to compute these things. And then we can look at these actually as a bunch of binomial processes. And let's suppose we can take a job and give it to 3 different Kubernetes networks. And then when they're all done, we can compare their answers. If they all agree on the answer, we can say, well, that seems like a valid answer. If one disagrees, we can say, well, that one's probably an error. Again, this is not perfect. If 2 disagree, or I should say, if all 3 disagree, then we have another problem. We reject all 3, but we can basically use an odd number of nodes or odd number of Docker containers to compute many jobs over time, and we can even do this on a sampling basis. It doesn't have to be deterministic, so that we can validate that which one is more likely correct. Again, it's not perfect, but it is interesting, and that ends up looking like binomial processes of 3 or 5 or 7, as long as you choose an odd number of redundant computations. That will, of course, drive up the cost or the carbon footprint. However, having 100 nodes are working on the same hashcash problem, or even 3 nodes working on the same hashcash problem, is just burning cycles that we don't know or don't appear to give any value other than their use in the blockchain. Here we're saying, hey, if you can prove you ran a virtual machine for an hour, then if you can validate it, the output of that running, then in fact, you solve somebody else's problem, and therefore they don't have to compute that in their own center or wherever they would. And we've done it, and we've used that to compute our own proof of work. Now, so there's a very nice paper that we're looking at as we speak. Oops, Bruin, Edwards, Bang, and Medvedovic. And so this is smart redundancy and distributed computations, and I'm looking at that with another group of students right now to see if we can actually utilize these values. So one of the things about this paper is they have several definitions. The most important one perhaps is this: total system reliability given R the probability of each job's success. I'm looking at R as being given the probability of each Kubernetes network computing it validly, or them not giving the job to a bad container, or not suitably pulling down the right container, or actually just trying to cheat us somehow. These Bruin et al. Point out that the total system reliability of R probability of each job success, or in our case, this would be R is the probability of somebody not faking their answer or giving a decent container to something. And they show that this is actually the binomial sum of the probabilities of 0 through k-1 failing machines. K being odd, this means less than half the machines would fail. So the total system reliability is the probability that less than half the machines fail. It means K is assumed to be odd, an odd number of machines. And so if less than half fail, then we're actually good to go. They give some other nice outcomes here. Like here's one of their algorithms where they say, okay, if K is odd, we need at least this many jobs, k plus 1 over 2 jobs to actually complete the job here. So in line 3, what they do is we try all k plus 1 over 2 elements, which k plus 1 over 2 is more than half of the elements. If those jobs all agree, we're done. If they don't agree, we just keep throwing a few more jobs in. That would be lines 5 and 6, and we update these values and keep trying until we get at least k plus 1 over 2 are done, or we go to line 8 and we're done. And we could never get enough people to agree on consensus, so that whole thing failed. I'm not sure what to do when the whole thing fails, but that is the idea. So the proof of virtual machine has some things we need to augment to make it truly a truly proof of work blockchain. But I think it's something along these lines. And one of the things I was very impressed by is we were really focused on taking off-the-shelf components. So Docker, of course, is off the shelf. Kubernetes is off the shelf, and Scupper is off the shelf. Again, Scupper and Kubernetes not consensus-based, but that could come about one of these days. So that's what we have.